Well, we've been concerning ourselves with rotational motion, movement around a circle, if you will, circular motion. So now let's take up the topics of angular and linear speeds. Now let's see, in this first problem we're looking at, first part of this problem, we're considering angular speed. Now angular speed is concerned with the number of rotations in radian in which a object moves over time. And we have a little formula for angular speed, which is omega, which kind of looks like a W. I'm not good at writing Greek letters, and that's going to equal theta over time. Angular speed, we're thinking about rotations of an object in radians over time. Now we see we've got a picture here of a DVD disc. It says it's 120 millimeters in diameter, but really I'm not concerned about that to find angular speed. So find the angular speed if the disc rotates at a rate of 3.5 revolutions per second. Well, I've already been kind of given my time because I want to find it in per second. And if I'm thinking about theta, we're talking about circular motion. Well, one trip around the circle is 2 pi. So if this disk is rotating at 3.5 revolutions per second, that means for every second we're going around the circle once, we're rotating a second time, we're rotating a third time, and a half. Well, what's one trip around the circle? Rotation. It's 2 pi. So in this case, this equation is pretty straightforward. We say that our angular speed, W, or omega, lowercase omega, Greek letter omega, is 3.5. We're going 3.5 times around the circle times 2 pi. And our time period, this is in per seconds, and our time period is in 1 second. What is the angular speed if we're going 3.5 times around a circle? Well, that's going to equal 7 pi, or just 7 pi over 1. Now, if I was asked to give that answer in an exact value, I'd leave it there as 7 pi. But let's just go ahead and do a conversion. Let's see, what's 7 times pi? 21.99, or actually, it's approximately 22.0. Didn't leave my room for my, let me do it down here, room for my radians per second. So my angular speed is approximately 22.0 rads per second. All right, that was pretty straightforward. The next problem we've got when we're looking at linear speed is going to be a little bit more complex. Now, linear speed, what does linear speed have to deal with? We're trying there to see how far does or how fast and what distance does the rotational motion represent. And you might think about that like tires. If my tire is rotating at so many revolutions per whatever the time period may be, let's say per minute, how far will that car travel? That's what linear speed is concerned with. So let's look specifically here at a problem. All right, so we got the same DVD. It's 120 millimeters in diameter. And we're told that this DVD player is overheated a little bit. The disc begins to rotate at a slower rate of 3.5 revolutions per second. Find the disc's linear speed in meters per minute. I've got a couple of conversion ratios I've got to do. One of those is my diameter here is 60 millimeters. Well, yeah, but let me get the formula first. So we got velocity, this linear speed, velocity equals S, which is our arc length, remember, over time. Now, so how do we find our arc length? Remember, our arc length, S, which we just did a minute ago, is the radius times theta. All right, so one conversion I've got to do is I've got to convert that 120 millimeters into a radius. So let's say that R right now equals 60 millimeters, but I want to express this in terms of meters. Well, let's convert this 60 millimeters into meters. So I've got 60 at times, let's see, how many millimeters are in a meter? Well, centimeters is 10, millimeters is 1,000. So right now I'm in millimeters, so my conversion ratio, what do I want to convert to? I want to convert to meters. Well, for every meter, there is 1,000 millimeters. So this is a meter, these are millimeters, these are millimeters, and you can see my millimeters are going to cancel. And so I've got 60 over 1,000, and that is going to equal, let's see, we've got a couple of zeros we could cancel out, right? Oh, I don't know, I'm just going to be careful. 60 divided by 1,000, rather than do it in my head, is 0.06 meters. All right, so 60 millimeters, which is the radius, half of that diameter, is 0.06 meters. All right, now I've got to find theta. This is my radius in meters. Now I need to find theta. Well, this thing now is spinning at 3 revolutions per second. And I'm going to go ahead and leave the seconds in here, and then I'm going to change that right now. I'm going to make that conversion from seconds to minutes a little bit later. But let's just quickly find the theta in terms of per second. Well, as we just learned on the other thing, let's see, if 1 revolution is 2 pi, this thing's spinning at 3 revolutions per second, and so theta is going to equal 3 times 2 pi, or 6 pi. All right, so now, what is my arc length, my S? Well, that's going to be the radius. S is going to equal the radius, which we said is at 0.06 meters, times 6 pi, let me put this unit of measurement, radians per second. Okay. Well, let's see. And radians is really not a unit of measurement. So we've got 0.06 meters times 6 pi. And I'm going to round this to the nearest, thousandth for the time being. So then my arc length is equal to 1.131 meters per second. All right, well, I'm close. I got to find meters per minute. Now, I've run out of room here, so I'm going to do this last conversion. And my time is just per minute, so I'm okay there. I'm going to do this last conversion so that we can get this per minute here in just a second. Let me move to another slide. All right, so we've got our linear speed is equal to S over time, and we have just determined that S is equal to, or actually this velocity is equal to 1.13 meters per second. And we got to convert that to minutes. Now, how many seconds are in a minute? And there's 60 seconds in a minute. And I want to cancel out this seconds and end up in minutes. That's what I'm wanting to find. So let me think about this. What's my conversion? Kind of stands my conversion ratio on its head. So if I want to end up in minutes, then I think I want to say there are 60 seconds per 1 minute. Now my seconds are going to cancel. My units of measurements are going to cancel, and I'm going to end up in meters per minute, right? So my linear speed then is 1.13, I think I said 1.131 times 60. And that's 67.86. I'm going to round that to the nearest tenth. And so my linear speed then is 67.8 meters per minute. That was a lot of fun, actually. So what we have to do there, we had to convert millimeters to meters. Well, we had to convert a diameter to a radius. That's not too bad, just divide by 2. We had to convert millimeters into meters. We then had to find theta. We had to find the arc length, the radius times theta. And then we had to turn around and convert that from per seconds into per minutes. That's pretty cool. Linear and angular speed. How about that?